Hello, everyone. My name is Sarah Cannon. I'm from Claremont McKenna College, and today I'm going to be telling you about fast and perfect sampling of subgraphs and polymer systems, which is joint work with Antonio Blanca at Penn State and Will Perkins at Georgia Tech. So just to start, let me tell you about the problem we're interested in. So in this problem, we are given a graph, G, that has n vertices. It has some bounded degree, so it has some maximum degree delta bigger than or equal to 3. You should think of delta as some constant. And it's also given some distinguished vertex R, which we're going to call the root vertex. And our goal is to randomly sample a connected vertex-induced subgraph containing the root R. And we want every subgraph S, which has, with a certain number of vertices, to come up with probability proportional to some parameter lambda raised to the number of vertices. So the regime we're going to be considering is when lambda is small. It's some small positive number, less than, say, about 1 over delta, which means that we want smaller subgraphs to come up with much higher probability and larger subgraphs to come up with much smaller probability. Right? When the number of vertices is large, the probability with which we want that subgraph to come up as our sample is going to be very small. So why are we interested in this? Well, this idea of sampling these vertex-induced subgraphs, which are called graphlets, is a fundamental task in areas like data science, network analysis, and so on. If you have a really large graph and you want to learn some things about it, you can learn things about that graph by looking at small sections, by looking at the neighborhood of one vertex, the neighborhood of another vertex, the neighborhood of another vertex, and so on. So by looking at these small pieces of the larger graph, we can get some idea what the graph itself looks like. It's also really important for sampling from polymer models. So I'll talk about that a little bit more later on. But polymer models are a very general class of models that have been very useful in a lot of situations. And an important subroutine in sampling from polymer models involves essentially this problem, sampling a connected vertex-induced subgraph containing a particular vertex. This has previously done with a computationally intensive enumeration step. With this new algorithm that I'm going to tell you about, we are able to skip that. So I am just going to jump right into telling you what our algorithm is for sampling a subgraph containing a particular vertex. So it's based on the idea of percolation. Right? So we first carefully pick some probability P. P is going to depend on lambda, and I will tell you a bit later on exactly how we pick P. But then we begin by letting our subgraph initially just contain the root vertex R. And then while there is some other vertex adjacent to our subgraph that we haven't considered yet, we're going to add it to S to our subgraph with probability P. Right? So maybe, for example, we choose for our root vertex R, the next vertex adjacent to it we pick is this vertex B. We generated a random number between 0 and 1. It happened to be that we added this graph to our subgraph. Maybe we look at another neighbor of our currently constructed subgraph, maybe this vertex B down here. For this one, we flipped a random coin and happened to not add it to our vertex S, so we mark it as excluded. It is not going to be included in our subgraph. So we keep doing this. Maybe we look at this vertex V next, and so maybe this vertex is added to our subgraph with probability P, so maybe it is added. And we continue looking at the vertices next to the subgraph we've created so far. So maybe we pick this vertex and happen to exclude it. And maybe we keep doing this. We happen to add this vertex down here to our subgraph, but all 3 of these vertices are excluded. And now we're done. There are no other vertices adjacent to our subgraph that we haven't considered yet. So we finish and we return this subgraph here. So this is essentially just running a vertex percolation process starting at R, including every vertex adjacent to the subgraph we've constructed so far with probability P. So when this probability P is small, like we saw here, this process might finish really quickly. Right? So this we are going to be excluding a lot of vertices. Our subgraph is probably not going to get very big before we have no more vertices that we can consider. However, when P is a lot larger, we might explore most of the graph. Right? This subgraph might continue propagating and end up including most of the graph. So because we are mostly interested in sampling small subgraphs, we are going to want to consider regimes in which P is small. Okay. So this algorithm is great in that it randomly samples a graphlet containing R, but it doesn't quite solve our problem. Right? So it samples the graphlets containing R with the wrong probability. Right? So if we look at this partial S being all the vertices that are not in the subgraph we've sampled but are adjacent to it, the probability of getting a particular graphlet S, well, we have to have included every single vertex that needed to be in there. Every single vertex in S we had to pick with probability P, and every single vertex adjacent to S but not in S we had to not pick with probability 1 minus P. Right? So this is the probability with which we sample a vertex, a particular subgraph S. But remember, we wanted to sample them with probability proportional to lambda to the number of vertices in S. So this first term looks good. That looks similar to what we wanted. But the second term with this boundary of S term is not what we wanted to have in our distribution. So the way that we are going to deal with the fact that this percolation algorithm gives us a subgraph with the wrong probability is to add one extra step into our percolation algorithm, which is a rejection filter. So we're going to do this percolation process, get a subgraph S, and then we are going to accept that subgraph with a carefully chosen probability here. This 1 minus P to the delta minus 2 times the size of S plus 2 minus partial S. So this minus the size of the number of vertices that are adjacent to S but not in S is really the key part here. So now when we look at the probability of accepting a particular subgraph S, we have this 1 minus P to the size of partial S, and we have a 1 minus P to the negative size of partial S. And so those are going to cancel. We are left with terms that only depend on the size of the number of vertices in the subgraph, not the number of vertices adjacent to the subgraph. And we end up with something proportional to, with this P times 1 minus P to the delta minus P raised to the power of the number of vertices in S. So when this P, 1 minus P to the delta minus 2, is exactly our lambda, we are going to get the correct distribution. And I will mention, by the way, this delta minus 2 size of S plus 2 minus partial S, this is carefully chosen to ensure that this is always a number between 0 and 1. Right? So it's chosen to make sure that this exponent here is always positive, so that this probability is always going to indeed be a probability somewhere between 0 and 1. Right? So when lambda is equal to this P times 1 minus P to the delta minus 2, we get the correct probability distribution. So that's how we pick this P. That's how we pick our P at the beginning of our algorithm. We pick a probability P so that this is satisfied, so that we end up getting the distribution that we want. So this algorithm works, first of all, when lambda is small enough so that you can find such a P. Right? If we had a really large lambda, we wouldn't be able to find a P big enough to make this, right-hand side here equal to lambda. But when lambda is small enough that you can find a P to make this work, that's when the algorithm is going to work. And this algorithm also takes expected constant time, right? When P is small enough so that this process terminates quickly. Right, so percolation processes, depending on the probability P with which you are including or excluding vertices, sometimes can go on for a really long time, sometimes can end very quickly. When P is small enough so that this percolation process terminates quickly, then this algorithm is going to happen in expected constant time. And it turns out this lambda being small enough so that you can find a P, and P being small enough so that the process terminates quickly, these are exactly the same threshold. So if we look at this critical value of lambda, this lambda star of delta, lambda as a function of delta, it's this delta minus 2 to the delta minus 2 over delta minus 1 to the delta minus 1. I will mention this happens, by the way, to be the critical point for percolation on the infinite delta regular tree, which in some cases is the hardest graph in which to sample a subgraph from. So for any values of lambda below this threshold, this algorithm works. It gives a sample, and I should mention, by the way, not an approximate sample, but a perfect sample. It samples a random graphlet. Remember, a graphlet is just a connected induced subgraph containing the root vertex R with probability proportional to what we wanted, this lambda to the number of vertices in S and expected constant time. And the constant in this expectation depends only on lambda and on delta. It does not depend on n, the number of vertices in the graph. This is because our process terminates much more quickly. It terminates so fast that it does not even explore the rest of the graph. It really just explores a small neighborhood around the vertex R. And I should mention that this is as big a range as we could possibly hope for. So it happens to be the case that when lambda is bigger than this threshold, If there were to be a polynomial time random sampling algorithm for this that found a graphlet and sampled it with probability proportional to lambda to the number of vertices in it, then NP would be equal to RP. Right? So we really can't hope for anything, any algorithms when lambda is bigger than this threshold. So our algorithm covers as wide a range of parameters as we could hope to. And our proof for this theorem is just a reduction from Reed, McFarlane, and Stefankovic, who proved the same thing for the sampling unrooted graphlets problem. So we just adopt their reduction and show that this is hard for the problem of sampling rooted graphlets as well, building on their work for sampling unrooted graphlets, where you just want a connected induced subgraph, but it does not have to contain any particular vertex. And I will also mention that we can extend our algorithm for the unrooted case as well. Right? So if you just wanted to sample a random graphlet with probability proportional to lambda to the number of vertices and expected constant time, we can do that. It improves on the algorithm given in this previous paper, which does this in polynomial time, but has a large polynomial running time. Polynomial in the size of the graph, the number of vertices in the graph. So our algorithm is in expected constant time under some assumptions we have to make about the model of computation. For example, our algorithm includes a step where you pick a random vertex of a graph. We are working in a computational model where we assume that can be done in constant time. Other models, one might assume that takes at least log n time to sample a random vertex of the graph because you have to at least write it down. But that is the most computationally expensive step here. Our algorithm for this essentially just picks a random vertex and runs our percolation process from that vertex. If the subgraph sampled is rejected, it just begins again, picks another random vertex, runs our percolation process at that vertex, and continues. Okay. So I'll mention there's another couple ways we can extend our result. I'm mentioning these in particular because this is getting us towards what we need to do to be able to apply this in the polymer model setting, which I will get to next. So the first is that we have been sampling a random graphlet S containing a root. We have not been allowing ourselves to sample the empty set. If we want to add that in, so we're sampling a random graphlet containing the root, vertex R, or the empty graphlet with no vertices, we can add that into our distribution. Everything works the same. We would just begin our algorithm by even just including the vertex R with probability P. Right, so with probability 1 minus P, we just return the empty graphlet, and with probability P, we include the root and begin the rest of our process just like before. This is important for polymer models because we're going to need the empty graphlet containing no vertices to be able to come up as one of our possibilities in our sampling. And I will also mention it's fairly easy to modify the probability that we want the probability distribution we want to sample with. So if there is some function f of s, that for every subgraph S has a value between 0 and 1. And this function can be computed in time polynomial in the size of S, and it is fairly straightforward to sample a graphlet with probability, this f of S, times our original probability lambda to the size of S. So all we do is just incorporate this f of S into our reduction probability. That's it. So we can modify our probability distribution by multiplying every probability by a number between 0 and 1. Everything still works the same. Okay. So now let me talk a little bit more specifically about polymer models and about subset polymer models. So a subset polymer model in a graph, you've got three things. You've got a set of polymers, each of which is a graphlet. So a connected induced subgraph of your graph. And we assume that the vertices are labeled with up to Q colors. Okay? And for every polymer, for every graphlet, it has a weight. And we also have an incompatibility relation. So we say two polymers are incompatible if they touch, right? If the union of these two polymers is connected. So essentially, polymers are compatible when they don't touch, when they are not adjacent. And so for some collection of pairwise compatible contours, so contours that where none of them are adjacent to each other, we can define a probability distribution over these polymers where the weight of a collection of contours is just the product of the weights of all the contours in that collection. And again, for these collections, we're only interested in collections of pairwise compatible contours. So this is really useful to study a lot of low temperature spin systems. So things like the Ising model, the Potts model, the hardcore model, and so on. We can think of polymers as describing the deviations from some ground state. So for example, suppose you are in the Ising model. You have a graph. Every vertex has a plus spin or a minus spin. And you're in the low temperature model, the low temperature regime, which means most vertices have, say, plus spins, and there's only a few vertices that have minus spins. You can define your polymers to be your connected components of minus spins, and then you can define a polymer model just like this, where the weight of a polymer is defined appropriately so that the polymer model and the Ising model have the same partition function. But really, if you take nothing away from this definition of subset polymer models, you should just remember you should think of a polymer as some sort of deviation from a ground state. Okay. And so our theorem here is that if we have a subset polymer model on some family of n-vertex graphs that have maximum degree delta, and we have lambda is small enough, so now it's not just less than the critical threshold, but because our subgraphs are colored, because every vertex in our subgraph is going to have a color, one of q colors, we need lambda to be a little bit smaller, less than 1 over q times our critical threshold. And if our weights of our polymers are bounded by lambda, bounded above by the distribution we just wanted to sample from, this lambda to the number of vertices in the polymer, and we have this extra condition on the weights here, which I'm not going to say too much about, but as long as this extra, or until the next slide at least, but as long as this extra condition on the weights are satisfied, then we can draw a perfect sample from the polymer model, and the expected runtime of our algorithm is n log n. So the key idea of how we do this is we use the polymer dynamics markup chain, which involves adding and removing whole polymers at random. But at each step, if you want to add or remove a polymer containing a particular vertex, previous algorithms had used enumeration, right? So enumerating all the polymers of a particular size containing a particular vertex, and then picking one of them at random. But that enumeration step can be costly. So instead, at each step, we use our algorithm. Right? So to sample a polymer containing a particular vertex, you just use the percolation and rejection sampling-based algorithm I talked about earlier. And then I will mention using some fairly standard techniques. So bounding chains, which is related to coupling from the past. Because our sampling of a polymer at each step is perfect, we can also use a technique related to coupling from the past to show that we get perfect samples overall, and that we can use this markup chain to get perfect samples. Instead of approximate samples. Most markup chains give approximate samples. We're able to modify this one very slightly using standard techniques to get perfect samples as well. Okay. So now I just want to say a little bit more about this condition on the weights of our polymer model that we have here and how it compares to other results. So I have this handy table here. So really, the sampling of polymer models is possible when the weights decay exponentially fast, and we need them to generally decay fast enough for various approaches to work. So some of the first work in this area using where the condition on the weights we needed was the Kentucky price condition. We needed these weights to decay like E squared times the number of colors times the maximum degree of the graph. Some other results recently have either improved the running time or improved the bound on the weights that you need in order to make this work. We are able to do the best of both worlds, have the most permissive bounds on the weights of our subgraph polymer model, and also have that fast running time. And in addition, all of these previous methods gave approximate samplers. We are able to give perfect samples from this distribution. And if you want to take a look at some of the previous works, I've included all these ones cited here down below. Okay. And so while I have stated our results in general in terms of subgraph polymer models, this can be immediately applied in some applications, such as better algorithms for sampling from the low temperature hardcore model and unbalanced bipartite graphs, and sampling from the Q-color ferromagnetic Potts model on expander graphs. We give improved algorithms in both of those settings. Those are the two examples we happen to include in the paper. But basically, anywhere you can use a subset polymer model to get a sample, our algorithm that was given can improve that process. So these are just two, but there are many other places in which this leads to an improvement as well. Okay, So just to recap everything that I have told you, our main contribution here is a new algorithm for sampling rooted graphlets. So a graphlet is a connected induced subgraph in a max degree delta graph. And we want to sample these with probability proportional to lambda to the number of vertices in that graph. When lambda is less than some critical threshold, our algorithm is based on using a percolation process and then a reduction filter. It gives a perfect sampler. It runs an expected constant time. And it works for as wide a range of parameters as we could hope for because it's hard when lambda is above this constant threshold unless MP equals RP. And the main application gives us fast, perfect sampling for polymer models, which apply for a wide range of parameters and give faster algorithms and a wider range of parameters that were previously known. Okay? Thank you.